pay close attention to the following aspect. Now, here is the scenario. What we have said so far is, if I have a flat fading channel with different SNRs, the way to get the maximum out of it is to do water filling. Okay, that is the result so far. So, this is what we have completely solved now. Now, I want to move over from here to the right side, where you have dispersive channels, where most of the practical channels that we encounter are of that category. So, the visualization of such a channel, this is frequency. Okay. So, you think of the channel frequency not as being constant. This is you can think of the channel gain. A frequency selective fading channel basically says that there is some variation in the gain of the across the frequencies. Okay. Now, if I had a scenario where my signal was this wide, right, that is when I see the frequency selective fading. All the frequencies in my signal are not getting the same channel gain. Now, I have a problem. Now, if I tell you, now please tell me what power to use, you say, well, I really can't tell you anything, because the result that we have is only if the channel gain is flat, right. If the channel gain was flat, then and I could have told you, you know what, currently the channel conditions is bad, use a low modulation scheme, if once the channel condition got good. Now, given this sort of scenario, the obvious sort of intuition says, hey, can you break this wideband signal into signals which are narrower in bandwidth. Okay. So, that is a visualization. So, basically I am going to say that, okay, this is the gain for this portion of the bandwidth, this is the gain for this, and now I ask you, okay, now I have got a wideband signal where the gains are all different. I am going to break them up into some number of subbands. Okay, so the total each of these, let me say that the bandwidth is B. It is much smaller than the total bandwidth that you have. Okay, so now I want to now ask the question, can you tell me what is the capacity of this wideband channel? I could not have given you an answer if it was a single wideband carrier, but now if I break them up into subbands, actually I can. So, I will tell you that the capacity of this wideband channel is the following. It is B, which is the bandwidth of each of those, summation over j, whatever number of such channels that we have, logarithm base 2 1 plus, very important, what is the gain, what is the channel gain that you see, or what is the SNR that you will see, the gamma, which is Ps by Pn, and whatever is your channel gain, magnitude h of j, it should be h of j omega, okay, continuous time frequency, magnitude squared, that is the gain that you are seeing. I am just going to write it as magnitude h of j. So, magnitude h of j squared times gamma. Okay. So, what did we do? I know how to get the capacity of a band of a signal with a certain bandwidth B, which has got a flat gain. This wideband signal, wideband channel, I broke it up into subbands, for each of which I could sort of make the assumption that the gain is flat, then I use the old formula. Okay. So, this is the now in the earlier case there was a f gamma coming because there is a probability distribution. Does that need to come here also? No, there is nothing probabilistic here. There are how many? There are some n channels. So, basically there is no PDF actually involved. Okay. Now, if no PDF is involved, does it still make sense to do power allocation? Does it still make sense? Answer is yes. Why? Because some of these channels are good, some of these are bad. So, why do you give equal power? So, the capacity formulation now can actually be enhanced to do the following. Okay. So, it is summation over the maximum of over the power allocation of these channels such that the summation of these power allocated to each of these subbands is less than or equal to the total power allocation. It is not P bar, it is a total power allocation P. Okay. So, now the objective function will be B times logarithm base 2 1 plus gamma times magnitude h of j squared, that is my this becomes my this actually now becomes my effective SNR. Okay. This multiplied by Pj divided by P, this is my optimum power allocation, and the constraint would be that sigma j Pj less than or equal to P. So, this is a quantity that will be less than will be a ratio which we can adjust, and the optimum power allocation, again I am taking it almost without any proof, that Pj divided by P will have to be of the form 1 over gamma naught minus 1 over gamma j with a plus sign, which is water filling. Okay. So, the key result is that when I have a wideband signal, first of all I am going to have frequency selective fading, and the process by which we will achieve capacity is I am going to quantize the SNR in each of those bands, okay, and I am also going to do 1 over gamma water filling. So, this is 1 over gamma naught, this is 1 over gamma 1 gamma 1 sorry 1 over gamma 1, this is the first subband, this is 1 over gamma 2 and 1 over gamma j. Okay. What is the power allocated? This one gets very little power, this one gets a lot of power, because that is a good channel. 1 over gamma 2 is small, means gamma 2 is large. This one gets no transmission, no power allocation, because you are above the water filling line. Okay. So, very interesting, a wideband signal where I can do some very flexible allocation, and I can even choose not to transmit at a certain power level, at a certain frequency band. So, now go back and look at the diagram. So, if I want to transmit a lot of data, I have option of doing a single carrier. Single carrier means what you see is the red line, but I cannot do power allocation, I cannot do I cannot exclude certain portions of spectrum saying, hey, you know what, currently the channel conditions are really bad in this portion of the spectrum, I am going to avoid transmission. I cannot do that. However, if I split it into these sub bands, I not only can exclude certain portions from transmission, for the remaining part I can actually do optimum power allocation and get you the maximum capacity out of this system. So, this is a very key observation. So, this is a way of getting your capacity, achieving capacity for a frequency selective fading channel. So, this is a mechanism for achieving capacity. Achieving capacity in a frequency selective fading channel. If you did not do this, really there is no way we can optimize for this type of achieving the capacity. You will get some throughput, but it will not be anywhere close to the throughput that you will get with this type of system in a frequency selective fading channel. Okay. Now, there is another dimension which is very important from the communication side. Let me just sort of highlight it, and then we will close there. Now, this has to do with the complexity in a dispersive channel, complexity of the receiver. So, basically we will just introduce this aspect, we will expand upon it in the next class. So, receiver complexity. Okay. Now, a very quick question. This is something which you would know. If I have no dispersion, this is what I transmit, this is what I receive. Now, supposing there is dispersion and I get this type of a signal at the receiver, what do I need to do at the receiver? I need to use a equalizer. So, a dispersive channel means equalizer is needed. Okay. So, dispersive channel means a equalizer is needed. Dispersive channel means equalizer is the only way I can solve this problem. Okay. Now, if I have L plus 1 taps in my channel model, that plus 1 says that is the signal that I am interested in. The remaining ones are previous symbols that got L plus 1 tap channel model. Okay. If this is my channel model, my received signal Rx signal contains L symbols of ISI. Okay, that is what it means, and I am sure you are familiar with this notation, L symbols of ISI. And in the equalizer domain of all the algorithms, optimal algorithm for equalizer, optimum algorithm for equalizer. Can you give me one of the optimum algorithms which you have studied, different types of equalizers, one of the optimum ones? It's called maximum likelihood sequence estimation, MLSE. Maximum likelihood sequence estimation. Okay. This is also known as the Viterbi algorithm, in case you are more familiar with that name. So, basically this is one of the optimal algorithm. There is one which is called maximum a posterior algorithm, but most of the receivers that we encounter actually implement the MLSE, maximum likelihood sequence estimation. This is also known as the Viterbi algorithm. Okay. The Viterbi algorithm has got a complexity which is proportional to the number of your constellation size. M is your constellation size raised to the power L, where L is the number of taps. So, M is your constellation size, this is constellation size. If it is BPSK it is 2, QPSK is 4, 16 QAM constellation size, and L is your number of symbols of ISI. Okay. So, here is a simple example and we stop with that. I have a 4G system, I have a bandwidth approximately 10 megahertz, that is my bandwidth of my signal. Now, bandwidth is related to baud rate, the number of symbol, number of times you use the. So, this is related to baud rate. Okay, it is related to bit rate also, but it is related to the bit rate through the baud rate times the number of bits per symbol is your bit rate. So, baud rate is a more fundamental quantity when you talk about the bandwidth. So, this is related to the symbol duration, right. 10 megahertz means I am sending approximately 10 million symbols in a second, which tells me that my symbol duration is approximately 1 over, let me just not say equal to, it is with pulse shaping and other things it will be slightly, but you can make it a fairly good approximation. This is 1 over 10 into 10 power 6, which is the same as 1 over 10 power 7, which is approximately 100 nanoseconds. That is your symbol duration. Okay. If I have a 10 megahertz single carrier system, this is what I will have as the bandwidth. Okay. Typical delay spread in a fading in a multipath channel is 5 microseconds. 5 microseconds. So, so if I transmit a symbol now, it will come after 5 microseconds. A copy will come, latest copy will come after 5 microseconds. This will show up. Now, in this period of time, how many symbols have gone by? I will have to take the symbol the delay spread 5 microseconds divided by symbol duration. Symbol duration is 100 nanoseconds. Okay, 100 nanoseconds. Okay, so approximately 50 symbols have gone by. Okay, and if I was using 16 QAM, my equalizer complexity with 16 QAM, equalizer complexity is going to be is going to be 16 raised to the power 50, mind boggling. Okay. So, this is the seriousness of the problem that we are encountering, notwithstanding the fact that if I transmit a single carrier system, I am not going to achieve capacity, I am going to have a tough time because the frequency is not flat. So, does multi-carrier, splitting the carrier into smaller frequency bands, does it help? Because it helped us achieve capacity, right? It helped us achieve capacity. Did it also solve the equalizer problem? We will answer that in tomorrow's class. Thank you.